So our last lesson, we looked at the tangent function, and we said that it was simply just a ratio of the opposite side over the adjacent side in respect to some angle in a right triangle. Obviously not the right angle, but one of the two other angles. And from there, we know that any right triangle that has that specific angle, any other right triangle that has that specific angle will be similar to it. Because of the angle-angle postulate, we know the 90-degree angle, we know one of the other angles, so we know they must be similar. So their sides will always be in the same proportions, and tangent just happened to be the ratio of the opposite side to the adjacent side of that particular angle. Today we're going to learn two more. Same exact thing, tangent is opposite over adjacent, and we've got two more to learn. The first one, and probably the most commonly used one, is the sine function. So it's pronounced sine, S-I-N-E. Usually when you see it abbreviated, it'll be just S-I-N, sin, but it is pronounced sine, and then cosine will be abbreviated C-O-S. So sine, cosine, and the sine is just the ratio of the opposite over the hypotenuse. So the ratio of the opposite leg to the angle over the hypotenuse, and then cosine is the ratio of the adjacent leg over the hypotenuse. So tangent is opposite over adjacent, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. And we're going to learn a nice fancy way to remember that in a minute. So in terms of what this looks like on a triangle, again, the sine of angle A is the ratio of the opposite leg over the hypotenuse. So we can write sine A is equal to opposite over hypotenuse, where obviously if this is angle A here, the opposite leg is going to be the one across. So there's our opposite leg, and then the hypotenuse is the one across from the 90-degree angle. And then cosine is just the ratio of the adjacent leg over the hypotenuse. So cos A is adjacent over hypotenuse, and that would be, this leg would be the adjacent leg, the one that makes up part of angle A but is not the hypotenuse. So we've got these three ratios that we can work with, and we'll actually find that as you get further into geometry and then into Algebra 2 and you learn more about these functions, they play a much deeper and important role in mathematics as a whole. But for the time being, let's just think about them as merely being sort of a shortcut, as if we had a similar triangle in our pocket at all times. So if we look at a right triangle and it has an angle of 28 degrees, we can pull our little sine, cosine, tangent charts out, or use our calculators and say, oh, I know a similar triangle to this triangle, and its sides have these ratios, so I know that my triangle here must have those same ratios. As we look at this, though, there are some statements that we can make about these functions based on what they tell us. And these sorts of statements, they call them identities. So the technical definition and equation that's true for all allowed values of the variable. So that means no matter what you plug in there, this statement is going to be true. Now, one of the ones that's kind of neat, if you think about it, if we're looking at angle A, and we want to look at the sine of angle A, the sine function we said is going to be the opposite over the hypotenuse. So that's this leg BC divided by BA. So if the sine of this is BC over BA, if we think about this angle B, well, we can find this angle, right? If this is 90 degrees, then this angle B must be 90 degrees minus A, right? The whole thing has to add up to 180. Here's 90. A and B together must add up to 90. So we can find angle B by subtracting from 90. So when we look at this identity down here, the sine of x is equal to the cosine of 90 minus x. Meaning, if we take angle A and we look at its sine, we get BC over BA. Well, if we look at 90 minus x, right, or 90 minus A in this case, we get angle B. Well, if we look at the cosine of angle B, cosine is adjacent over hypotenuse. Adjacent is BC, hypotenuse is BA. So we're essentially just looking at the 90 minus x tells me instead of angle A, I'm looking at angle B. And here we're doing cosine instead of sine, so I'm doing adjacent over hypotenuse. Instead of here, I was doing opposite over hypotenuse. So we can see that that will always be true for every right triangle. The sine of x of some angle is going to be equal to the cosine of 90 minus that angle. So that's an example of an identity, and again, you'll see more identities as you get further into math. Now, I did want to bring up, at this point, we have our three major trigonometric functions that we're going to learn, and there is an easier way for remembering, and this has been taught for years and years and years. I learned it when I was in school, this idea of SOHCAHTOA, and you may have heard this before, you may have heard me mention it, you may have heard it in other classes, but SOHCAHTOA is a nice easy way to remember that the sine function is opposite over hypotenuse, the cosine function is adjacent over hypotenuse, and the tangent function is opposite over adjacent. So sine SOH, so sine is opposite over hypotenuse, CAH, cosine is adjacent over hypotenuse, TOA, tangent is opposite over adjacent. And another neat thing that we can see is that the tangent is technically just the sine divided by the cosine. Because if you put opposite over hypotenuse divided by adjacent over hypotenuse, the h's cancel and you're left with opposite over adjacent. So that would be another example of an identity that we said will always be true. The tangent will always be equal to the sine over the cosine of any angle. So something to keep in mind. But this SOHCAHTOA, back when I was in school and people were much less culturally sensitive, there were cartoons of Native Americans in their full tribal garb dancing around a fire chanting SOHCAHTOA, SOHCAHTOA, and things like that. So I mean there were tons of posters and it was all over the place. So it definitely does make it easier to remember, and I still, even to this day, when I'm doing trig stuff, I have to pull out every once in a while and go, okay, SOHCAHTOA, so cosine is adjacent over hypotenuse, alright, and then I proceed from there. So keep that in mind, maybe write it down somewhere that you can keep handy until you really feel like you have it down. So let's look at some examples of how we can use these. It's pretty much just going to be the same way that we use tangent, but now we're just looking at different legs that we did than we did when we did tangent. So here they want us to use the triangle. They want us to find sine t, cosine t, sine g, cosine g. So if we look at sine t, we said SOHCAHTOA, sine is so opposite over hypotenuse. And so if we look at t, and we look at the opposite side is 12, the hypotenuse is 20, so we can reduce that down to 3/5. If we do cosine t, we look at cosine, now we have adjacent over hypotenuse, right? SOHCAHTOA, C-A-H, cosine adjacent over hypotenuse, we get 16 over 20, right? Because here's the adjacent side to angle T. 20 is obviously the hypotenuse. We reduce to 4/5. Now we can go take a look at the other angle. And remember we said there is a relationship between these two. As this one gets bigger, this one gets smaller. So we're going to see something interesting here. When we look at the sine of angle G, right, here's G, so the opposite would be 16. Hypotenuse would be 20. So we get 16 over 20, or 4/5. And then cosine adjacent over hypotenuse, we get 12 over 20, or 3/5. So again, if you notice here, the cosine of this angle is equal to the sine of this angle, which makes sense. Going back to that identity from the first page, this angle G is just 90 minus this angle T. So the sine of this angle is equal to the cosine of 90 minus this angle, which is G. So neat little relationship between the two angles in a triangle when we do these ratios. Alright, you're going to see lots of these problems, and actually the next lesson that we do, 8.5, is going to have pretty much all problems like this, practical problems using angles of elevation and depression. So we'll get into those next time, but just a similar example here. We have a 20-foot wire that's supporting a flagpole that forms a 35-degree angle with the flagpole. So here's the flagpole, here's the wire that's supporting it. They want to know how high the flagpole is. So from here, we know that this is a 90-degree angle. They mark that. It's always going to form a right angle with the ground. So the wire serves as the hypotenuse for this triangle. Because you know an angle and the measure of its hypotenuse, you can use so if we have this angle and we have this hypotenuse, what are we trying to find? Are we trying to find the distance on the ground or the height of the flagpole? Here the question asks us, how high is the flagpole? So in reference to this angle 35 degrees, we have the hypotenuse and we'd like to know the adjacent leg, right? This would be the opposite, this would be the adjacent. So we want to know the adjacent leg. So we're going to use adjacent, and hypotenuse is cosine, right? Adjacent and hypotenuse. So cosine of 35 degrees is going to be the height of the flagpole over the hypotenuse, 20. So from there, we want to solve for height, so we'll multiply by 20. And just be careful, you cannot multiply 20 by 35 and then take the cosine, right? When you do cosine and sine, it's very particular that, if you have an angle in there, you have to just leave it at that angle, do the cosine of that angle, then you can multiply it by some value. So do cos 35 in your calculator, then multiply by 20. You'll get 16.38, or about 16 feet tall if we're rounding. All right, one more example here. Using the inverse, just like we did with tangent, we can do the inverse of cosine and sine as well. So here we have a right triangle. One leg is 1.5, the hypotenuse is 4, and they want to find the measures of its acute angles to the nearest degree. So anytime we're finding the angle instead of the length, we're going to have to do inverse tangent function, right? Because we're going to be solving for the angle in here instead of using that angle to solve for one of the sides in the ratio. So in this case, we have the short leg and we have the hypotenuse of this. So in this case, they're saying we're going to find A. So if we're finding angle A first, that means we have the adjacent leg and the hypotenuse, right? 1.5 and 4, and so adjacent and hypotenuse, we want to make sure that we use the cosine function. From there, we can divide 1.5 and 4, get 0.375. So that means that the cosine of whatever this angle is going to be equal to 0.375. So at this point, this is where we need to use inverse. This is something that you have to use a calculator for. Again, these cosines and sines and tangents and inverses, you're all going to have to use the calculator for it. So we do the inverse cosine of both sides, which leaves us just with A. And then over here, we get the inverse cosine of 0.375, which when you punch that into your calculator, you get 67.97, or to the nearest degree would be 68. From there, two ways. One, we could go back and set up another cosine or sine function to try to find angle B, but that might be a lot of work. At this point, if we know this is 90, if we know this is 68, we should be able to just use the fact that the acute angles are complementary. A and B have to add up to 90. So if A is 68, then B must be 22 once we subtract. So those acute angles are going to be 68 and 22. All right, that's it for this lesson. Again, the quick checks are for yours to do on your own. Make sure you have those done for class tomorrow, and we will do some additional practice with this later.